So our papers today are gathered under the title Mathematical Expeditions in quite a neat sequence from the 16th to the 18th to 20th centuries. And what I want to begin by doing is to trespass a little, possibly trample a little on the territory of the other speakers this afternoon, because there are very different senses of mathematical expeditions. So in 1919, the expedition that we'll be hearing about later, and other ones too, were done with the purpose of testing the predictions of Einstein's general theory of relativity. 18th century expeditions, for example, those to measure a degree of the meridian, such as that of La Condamine and Bouguer to Peru, and the other one that went to Lapland, were intended to resolve the controverted question of the figure of the Earth, the shape of the Earth, whether the Earth was squashed at the poles or at the equator. And at issue there were competing predictions from Newtonian and Cartesian theories of gravity and the Earth's shape. So those 18th and 20th century expeditions had as their principal purpose an effort to tackle a theoretically motivated question using precise measurement. Other expeditions in the 18th century were not necessarily intended to adjudicate between competing theories, but nevertheless had as their principal stated purpose the accomplishment of new measurements and the acquisition of new knowledge. So Cook's first voyage, famously, was publicly stated to be to go and observe the transit of Venus in the Pacific and thereby better determine the distance between the Sun and the Earth. Now, if we come into the 16th century, then expeditions then were not undertaken for the principal sake of mathematics or of science. The driving imperatives were things like trade, plunder, and settlement. So that's not, you might think, such a promising environment to be thinking about mathematical expeditions. But it doesn't mean that we need to entirely relinquish that term, mathematical expeditions, because through the still novel claim that mathematics should transform the emerging practice of oceanic navigation, mathematical expeditions did have a contemporary 16th century meaning. And to think, what did that mean in practice? It's good to go to the very beginning of the 16th century and just take briefly the example, not from England, as I'll be coming on to, but from Spain. From the nomination of Amerigo Vespucci, after whom America is named, Vespucci's commission as Spain's pilot major, the chief royal pilot in 1508. And that commission required him to examine pilots for their navigational proficiency, particularly in the use of the quadrant and the astrolabe. But he also had responsibility for the assembly, for the construction of what was called the Padron Real, which was the master chart, the master sea chart, whose role was to accumulate the observations of mariners, the diverse charts that are already being constructed of different parts of the world, and to resolve any differences that there were between charts, in order to make the one template that could be used to generate reliable copy charts that would give navigators confidence that they could safely reach parts of the world knowing that they were building on a kind of legacy and accumulation of knowledge and experience. So with Vespucci, he was named by the Crown, so this is a state appointment. It becomes an institutional commission, the Casa de la Contratación in Seville. So we have a place, and we have a person, and we have a set of responsibilities. And for most of what I'll be saying, I will focus on those two parts of Vespucci's role, testing pilots for their knowledge, their understanding, their expertise in the use of instruments, in his case, the quadrant and the astrolabe, and also in this cartographic role, assembling, in his case, the Padron Real. So those will be the charts, maps, and instruments are going to be my main focus, and that is absolutely in the 16th century what mathematics is seen to be about. Now we have typically since the 19th century, the idea of mathematics as being the queen of the sciences, the most abstract of the sciences. In the 16th century, mathematics is typically seen as being a very hands-on, almost mechanical, lower status subject, and instruments and charts are absolutely part of that. So having set out that contemporary 16th century vision of what mathematics is, the kind of things that we can look to under the heading of mathematical expeditions, I just want to give you a little heads up that at the very end, I will come back to that question of theory in relation to expeditions and the way that it's not, it isn't totally removed from the 16th century context. We can see the ways in which some theories, some contemporary natural philosophy could be tested in an expedition setting. So there's a little bit that feeds into those 18th and 20th century stories. So by introducing Vespucci in the Spanish context, that gives us something where we're talking about an institutional setting, a state setting, and actually that's rather different for the English context that I'll mostly focus on. Because for England, there were not state institutions. There were not pilot majors. There was a hope to create that role, but it wasn't successful. And there was therefore not that organized, state-centered regulation of the training of mariners, the creation of cartographic resources. English initiatives in the 16th century, in the second half of the century, were pursued on a much more individual level. They were typically under either aristocratic or merchant patronage, and in that context, which wasn't totally removed from the state, there were some connections, but under that more individual setting, a number of quite serious senior mathematicians went to sea to personally assess and reform navigational methods and instruments. And I'm going to be focusing on Edward Wright, but just to mention, he's not the only one. There are others. None of them may be household names now, but in the period, they are seen as the sort of leading figures in the English context. So one has a figure like Thomas Digges, an often rather imperious gentleman mathematician who decries the errors of mariners in 1576. And states there needs to be a reformation of these erroneous practices that mariners themselves use. He finds that he is rebuffed by mariners. They say, well, whatever you say with your fine mathematics, our ways work. And so Digges says, well, in that case, I'm going to sea, and I'll sort of prove you wrong. And he goes to sea for 14 weeks and comes back vindicated, he says. He demonstrated that his detection of errors, his proof that he could come up with better methods was absolutely the case. And this was the way to do it, using mathematical methods. Unfortunately, we know nothing more than that. He just says he did this. He promises to provide a book on the improvement of navigation, but it is never published. Other English mathematicians who had a significant role at sea would include Thomas Harriot. He is recruited as a university graduate by Walter Raleigh, and Harriot assisted in the training of Raleigh's pilots in advance of the famous voyage to Virginia. And Harriot went on that expedition. He spent 1584 to 5 in Virginia, but even though he had that direct experience of the art, his navigational treatise is lost. We know he wrote one. And the only text to come out of this expedition to Virginia is a narrative description that talks up the wonders of this newfound land to try to encourage its promoters to get a reward from more people going there to colonize, to set up a permanent settlement. So with Harriot, you have again a very promising setting, this very able mathematician, but we don't know the detail of what his experience was at sea, how he went about his work. And that's why I'm coming on to Edward Wright, because here's someone for whom we do have evidence of detailed engagement in a voyage. And we have evidence with Wright, partly because not only does he go to sea, but he manages to write and publish a text on navigation. That's a significant one. So it's a book that was published in 1599 called Certain Errors in Navigation. And at the bottom of the title sequence, it says, "They have been detected and corrected by Wright." And he gives a little outline. It's to do with the sea chart, errors in the sea chart, and the use of the compass, the cross staff, tables of declination of the sun that you use to work out your latitude, and of the fixed stars. If you want a bit more on that, this is an alternate title page issued with a different publisher, where it's spelt out in a bit more detail just what these errors are that he is detecting and offering the means to correct. So that's a major text. It's recognized at the time as being important and has been recognized subsequently too. It came out in a second edition, 1610, dedicated to James I and VI's son, Prince Henry, and that was clearly going to be setting up Wright for some significant patronage. So who was this person, Edward Wright? Let's just give a very quick overview of his career. He comes from a sort of middling family. He goes to Cambridge as a student, becomes a fellow, Gonville and Caius College, but he has an unusual career because he has diversions from that academic career. He goes off to sea with the Earl of Cumberland in 1589, and we'll come back to that. But also he sets up a significant program of observation in London in the mid-1590s, so doing serious astronomical observation, positional astronomy, observing the sun particularly. And he resigned his fellowship in Cambridge and then carved out this innovative but precarious career in London. He was an author, so writes on navigation. We saw certain errors, but also writing on astronomy, on sundials, logarithms. He has a significant role in bringing that out into the public sphere. He writes on magnetism, and also he is a very active kind of technical consultant. He's involved in a project to bring water to London. So he's very active and engaged, trying to make a kind of plausible, resilient career for himself in London. And as ways of making that work, he appeals to highly placed patrons, such as Prince Henry, but is latterly also employed by the East India Company. So both aristocratic and royal patronage, but clearly some mercantile patronage as well. And clearly what I want to focus on is this sort of adventure going off to sea with the Earl of Cumberland. And Cumberland, a nobleman, a significant courtier, so this might seem rather sort of flamboyant thing to be doing. You know, this is a kind of cool guy to go to sea with, if he can be a courtier with Elizabeth's champion. And it's very different from the kind of context of privateering you might imagine. What exactly is that? Well, that it's an activity that is licensed by the Crown, which issues what are called letters of marque, and it allows the bearer of one of these letters to seize shipping as a reprisal for claimed losses already sustained. And that gives what was often a very thin veneer of legality to what became very indiscriminate attacks on shipping of foreign nations. And of course, those would then generate further retaliations, and you had a continual cycle of reprisals going between different states and different figures. And Cumberland becomes a major figure in this privateering world. He has a series of almost annual voyages with small fleets that he outfits himself. He creates his own ships. He rents ships from the Royal Navy to go off and to annoy particularly Spanish shipping, but others too. And it's on one of those voyages that Wright is taken. It's a voyage to the Azores, 1589, and what Wright does is to provide a narrative of this voyage, which is an appendix to his book, Certain Errors. And that narrative itself is not a mathematical account, but it's a tale of the prizes taken, the notable military events such as the storming of a fort in the Azores. And if we want to see Wright at work as a mathematician, we can do that through his reformation of the sea chart. And the volume Certain Errors contains a large fold-out map which depicts the 1589 voyage. And this chart is its main notable feature from the point of view of history of cartography is that it's a working Mercator chart. It's the first of its kind, the first printed, published one, based on that projection that Gerard Mercator had published in 1569. And when Mercator published his new projection, it appeared in the form of a gigantic wall map, many, many individual sheets that are printed. You probably can just about, this is Africa here, South America there, Europe up there, British Isles are just there. It's a bit hard to make out the features of it, but it's a new projection, and one that Mercator says is especially for the use of navigators, because its principal feature is that for a constant bearing, a constant direction by the compass that is sailed by a ship, that appears on this new map projection as a straight line. And that is what Wright is producing, and he's having to do it from scratch. He knows it's possible because he's seen Mercator's map, but Mercator gave no instructions. How do you make one of these? He says nothing about that at all. You simply get the graphic image of his world map. And in Wright's Certain Errors, he provides the mathematical basis for creating this Mercator chart, and he shows it can be done through making his own chart of the voyage to the Azores. Now, that gives a real sense of novelty to the cartography that Wright's providing, and so it might therefore seem a bit disappointing when one looks at the navigation of this 1589 voyage itself. If you zoom in on this, there's a little bit, I hope you can see that there's some text here, exitus and reditus, with some little dotted lines. And if you can't read it, I hope that makes it a little bit clearer. And if you colour in the dotted lines, it shows you the way out and the way back. And so the way out looks like this. And if you think that looks rather straightforward, sail down to Spain, take a sharp right, and go and hit the Azores, then the way back is also in exactly the same format. That's called latitude sailing. You sail to the latitude of your destination, and then you go along until you arrive at or possibly strike your destination. There are several points to make about this and the practice of navigation that it represents. First to say is that Wright was not responsible for this particular course. He would have been an observer on this voyage, seeing what is going on, but not setting the course, not in charge of the practicalities of navigation. And if you think it looks simple-minded as a way of sailing, actually it was quite advanced at the time. But this is not an exercise in the most advanced navigation. The reason that this course is chosen is entirely about the aims of the voyage, because the greatest ambition of the Earl of Cumberland's fleet was to intercept the Spanish treasure fleet on its way back from the Americas. And since the route of that fleet was from the Americas to the Azores and then sail straight over to Spain, then in order to maximize your chances of success in this privateering voyage, what you had to do was to make sure that you were going to be in the way of this fleet. Where exactly was it? You would sail in exactly that single latitude sailing between the mainland and the Azores, and if you didn't find anyone, then you would cruise around the Azores in the hope of gathering intelligence or stumbling on a profitable prey to try and attack. So this is not about exercising maximum navigational skill. It's about trying to make sure that you can be a successful privateer. Nevertheless, Wright's exposure to the conditions of navigation at sea was absolutely key to the series of reformations that he provided in his Certain Errors navigational text. But that text gives us very little sense of how Wright pursued his mathematical agenda on board ship itself. However, luckily, we have another opportunity to witness Wright's experimental and investigative approach at sea. Because although if you consult standard secondary sources, they will confidently say that Wright went to sea in 1589 and never returned there after the 1589 voyage, actually, he did go back to sea. He went back to the Azores with another voyage with the Earl of Cumberland 4 years later in 1593. And before looking at the remarkable evidence that survives from that second voyage that Wright took part in, it's worth reflecting on the experience that Wright was committing to. Because his voyage in 1589 had been absolutely no summer holiday of sunny days in the Azores. This was a very serious and risky business to get involved in. On that voyage of 89, the fleet ran out of water. It ran out of anything else to drink too. And it wasn't until they were caught in storms near the coast of Ireland, you can see the little loop that they performed there, where they had the misfortune to be in a storm, but the fortune to be in a hailstorm. And everyone collected hailstones to melt them for the water because they were that desperate. So Wright was under no illusions about what going to sea meant in this period. He writes of that particular experience. In every corner of the ship were heard the lamentable cries of sick and wounded men, sounding woefully in our ears, crying out and pitifully complaining for want of drink, being ready to die, yea, many dying for lack thereof. So as by reason of this great extremity, we lost many more men than we had done all the voyage before. This is not something that you enter into with a skip in your step if you've done it once already. And he continued to reflect in that way that when you went to sea, you were banishing yourself from your nearest friends and native country. You're in a wooden prison, always within one span of present death. So he's absolutely doing this, knowing what he's going into, and there therefore has to be significant benefit to be possibly persuaded to go back to sea. So what do we know about this second voyage that he goes off to in 1593? Well, the evidence for it is recorded in a volume of Wright's, a manuscript volume of Wright's at Trinity College in Dublin. And in it, there is a narrative by Wright himself and additional narrative material from one of the fleet's captains. But the most telling section for our purposes today is a tabulated traverse book or log. It's the two sheets, that's two images stuck together it's too tightly bound to take it as a single spread, but it is in the form of a single spread. And this double spread, in this tabular form, contains a great deal of information from June to September 1593. It's in the format that was just being established by leading contemporary navigators such as John Davis. And when we dive into it a little bit further, you can see up at the top there is August, so you get a column of dates. Then beside that you have place and course. So if you can see land, you make a note of where you are in relation to the land. but then you write down your course when you're out at sea, so you can see northeast by north over here. The number of leagues that you sail on any one bearing. There are some scattered observations of the variation of the compass. We'll come back to that. And then there's the height of the pole, the latitude that is being instrumentally observed. And then the last one is the direction of the wind. So you're tabulating all that information that gives you the basis for plotting your voyage on a map. And you can see this is not a kind of neatly polished account. These are rough notes with errors and emendations, and even alterations in the format of information being recorded. And most strikingly, I would say, the level of detail that appears on this table increases towards the end of the voyage, particularly in recording the latitude. So we have the height of the pole column here, 39 degrees, 48 minutes is being written down there. If we move on, this is the latitude column here, and you'll see, in addition to numbers, there are some little symbols. There's a little funny, is that a sword? Is it a cross? There's a little star up here, another star down here, another cross. If you can't see that well enough, we can go into extreme detail, possibly excessive detail, and again, so you can see there's a little cross here and a little star up there. That gives us something to think about, what's going on there. Well, we get some further prompting, some further stimulus. Here's further on in this log of the voyage, we have some other symbols down in this column. Let's go in a bit closer. This time we've got a little ring here and a circle with a dot, another little ring with an extra one on top, and then a little sun with the rays of the sun streaming out. Well, what we're seeing, I think, is this one here, that one there, all the way back to there. When we look at this, what I think we're seeing is Wright recording the instruments that are being used to make the measurements. So that's what were then standard instruments, the cross staff in that cross form, and the circle of the mariner's astrolabe. But what is really intriguing and is worth picking out in terms of Wright sort of innovating and experimenting here is that it's not just those familiar shapes that appear in his log. So if we move on, again, we have these latitude observations, and if we go in closer, you'll see we've got a cross here, so I'm saying that's a cross staff being used to measure the height of the sun. Here's the mariner's astrolabe being used to measure the sun, but at night time, a star is being observed with something else, a bit like an anchor upside down. And what is extraordinary here is that that is not, at the time, that isn't a recognized instrumental form, but in the second edition of Wright's book, right on the title page, here's an instrument here, which is shown in the book as, he calls it his C quadrant. That is published in 1610, but Wright seems to be using it in 1593. So that gives a sense that in this 1593 voyage, Wright is trialing a new instrument at sea, and that he is deliberately comparing the performance of different instruments. And for such an early date, it's remarkable to have such sort of raw evidence for both innovation and testing in the practice of this new mathematical form of navigation. And Wright, who says that he has already drafted his book before he goes off on this 1593 voyage, it appears then that he is taking things to sea in order to test, to trial, and to put improvements into practice under his noble patron. So that's novelty in both instruments and cartography as a way of rendering expeditions mathematical. But just to come at the end, towards the end now, I want to just say a little bit about the testing of theory that I mentioned right at the start. In contemporary 16th century terms, what that means is looking at the way that mathematical practices can be brought to bear on what was called philosophy or natural philosophy. And so I'm going to end with looking at the case of magnetism and the way that there is a whole philosophy of magnetism that is being brought to bear here. And what I hope that will show is that beyond these mathematical techniques, there are some larger questions at stake. They are not being promoted as the sole purpose of voyages, but for the mathematicians on the voyages, there's an opportunity to be investigating some large-scale new ideas. And so the issue at stake here appears in navigators' terms as what is called compass variation. So on Wright's title page, he talks about the second error to correct is the error of a whole point of the compass, and more many times by neglecting the variation of the compass. So what is that variation of the compass? In a little manual by a compass maker from 1581, Robert Norman, he explains this compass variation as the difference between true north, the line showing the pole, and magnetic north, the line respective, the line that the magnetic compass actually points towards. And the difference between them is compass variation. And Norman shows that if this is true north going to the geographical North Pole, then you will have true east and true west, but there will be a false east and a false west given by the compass. So you have to be aware of that if you want to plot yourself correctly on a map. How to account for this phenomenon of compass variation? Well, there were a lot of different discussions and solutions proposed. One of the most disseminated ones was again by Gerard Mercator. This is an inset map of his showing the North Pole here. There's the north of Scandinavia. This is Russia here, with these hypothesized lands around the North Pole. Mercator says you can explain this strange variation of the compass, the fact it doesn't point to true north necessarily, by there being a magnetic pole, and that's this thing in the sea over here. So if you're here, your compass will point to true north because it goes through the geographical pole to this magnetic pole. But if you're over here, your needle will point that way and not this way. So here's an explanation, a global explanation of how this phenomenon comes to be. Mercator seems to recognize that there are challenges to this. In addition to this magnetic mountain that he has just here, there's another point just there where he says, well, that's where it seems to be this magnetic pole from other observations. Maybe not all the observations are entirely harmonious. And the big challenge that comes is from more observations that make it harder and harder to see that Mercator's theory can be right, that there's a single pole that everything will point towards. And the possibility of a regular global mathematical theory of this compass variation is challenged by increasing numbers of skilled observers reporting observations of this variation. That lack of regularity was then put to use, put to intellectual work by a contemporary natural philosopher. So William Gilbert, in his 1600 book, De Magnete, comes up with a novel way of accounting for this variation, because Gilbert says the whole Earth is a great magnet. And therefore, by experimenting with little spherical magnets, you can see how the behavior of the whole Earth should be. And Gilbert says, if you imagine a continent like this, because the Earth is magnetic itself, little needles will point towards there. They won't point to the true pole. They will be deflected towards great land masses. So Gilbert has an idea of how to explain the apparent irregularity of this compass variation. That is something that Wright was extremely familiar with. Wright has the very unusual role of writing a preface to Gilbert's book. There are contemporary sort of gossipy comments that Wright wrote parts of Gilbert's work that were too mathematically demanding for Gilbert to manage by himself. So he was definitely closely involved in this. He knew about Gilbert's work. And what is interesting with Wright is that he tries to put the collection of this data into a form that you can see, you can test whether Gilbert's ideas are correct. So he shows this variation of the compass on the chart to the Azores, 1589. There's a little detail there with two particular observations at sea on those dotted lines of the way out and the return. And for Gilbert's point of view, this is encouraging. So this is near the coast of Spain and Portugal, or rather, yes, it is, yeah. And it says it's an easterly variation. So the needle is pointing towards the landmass. Wright takes this much, much further. In 1610, he revises his book, and he has a whole world map on a Mercator projection. And when you zoom into that, you see that there are dotted around in the sea. There's Britain up here, Spain, the Azores there. There are little marks in the Atlantic. And he says that the numbers scatteringly dispersed here and there are observations of this variation. The letters east and west show which way the needle points, away from true north, but he also gives you the witnesses for this. So if it says ED, it's an easterly variation observed by John Davis. So you get a list of reliable navigators who can show you exactly what the variation is at different parts of the world. So here's the Azores with some observations. There's one which is 0 east there from Hull. As you go across the Atlantic, very reassuringly for Gilbert, the variation turns westward, pointing towards the landmass of North America. So that seems quite promising. Unfortunately, in the South Atlantic, when you accumulate the observations, so here's Africa and Brazil, they remain eastwards as you get towards the South American coast. So Gilbert's rule, this philosophical explanation, doesn't work for the South Atlantic. And because Wright is so involved in Gilbert's work, he absolutely knew about this. He does not make a large explicit comment on this. This falsifies Dr. Gilbert's rule. But it's inconceivable that he wasn't aware of the implications of drawing up a map like this and populating the world with these observations of skilled mariners. So it's not explicitly stated, but I think we can be very confident that Gilbert's ideas were being challenged ultimately as Wright accumulated more observations. So, with trusted observers, any expedition could therefore provide data. And although I've used 16th century terms to present the understanding of mathematics and Wright's endeavours here, to lapse into anachronism for a final comment, what we're seeing is what you might think of as a much more characteristically modern endeavour here. This is a kind of crowdsourcing in order to provide the data for looking at global theories of the Earth and magnetism. And that means that you do have to have a question. How can you trust the observations of these navigators? But that's a very modern question, and it's one that I think Wright and others at the time are trying to grapple with. So they're doing what we see as this modern form of mathematics, but they are taking it to make contact with, to challenge aspects of contemporary philosophy. So there is, even if not in the explicit aims of the voyages, there is a will and a wish to tackle theoretical questions in these mathematical expeditions. Thank you.
On the compass variation point, I mean, how would they know what true north was?
So there are different ways of doing it. Some people make special compasses that don't just have a compass card with a needle underneath it, that's the normal form in a ship. So all you see is this rotating compass card. So there are some bare needle compasses that are made, and you can take an observation in the morning and before noon and one afternoon, and then you can get your north line. That's easiest on land. There are other ways of doing it by where the sun rises, the sun's amplitude, where it rises or sets, because you can work that out from tables where it should be, and then you can establish the difference between true north and what the compass itself is pointing at. So there are a number of ways for both land observations and sea observations. That it's not necessarily simple. You know, you're at sea, you're on this moving platform. In Wright's notes, this is not something that happens every day. You know, that there are some observations of the variation, but I think it was probably quite hard to do. Certainly in 1589, he looks like he's got quite precise observations when they're printed, but in the same manuscript there are the manuscript notes from his 89 observations, and you get to a sort of seemingly precise value by averaging over several different ones, which are all to a sort of half a point of the compass or something like that, so they can be quite crudely done, it seems.
You mentioned at one point that you had to avoid the Spanish fleet.
Not avoid it. You want to encounter it. You
yes, I mean,
you want to get in its way.
I see. So it was not in danger of being, a piracy or anything like that.
It isn't being a pirate because it is legally sanctioned doing this. But it's, as I say, it can be a rather thin veneer of legality as to what is going on. Because certainly on a number of these voyages, other ships are seized, sent back to England, and their cargo is confiscated. And then later on, you have court cases that come through because it was a Dutch ship, and their owner makes a claim against the English Admiralty.
So they're flying under the British flag, yeah?
Or
this one was.
Yeah,
yes.
and at that point, the English flag, yes, yeah.